Welcome back to graphing the reciprocals of primary trig functions. This time we'll explore the reciprocal of cosine. So the function y equals secant x. So what you're seeing here is the graph of cosine function. I drew two periods of it, or two cycles, from negative 2 pi to 0, and one cycle from 0 to 2 pi. The main features of cosine function are period length is 2 pi radians. It has maximums of 1 and minimums of -1, and 2 x-intercepts will appear in every basic cycle. So the x-intercepts are at the indicated points. So we'll build the graph of its reciprocal based on the same principles as we did the graph of the reciprocal of sine, so the cosecant function. So we'll start off with the x-intercepts of cosine. At the x-intercepts, the cosine function will have a value of 0. Therefore, the secant x, which is 1 divided by cosine x, will be equal to 1 over 0, which is undefined. And we said that when the function is undefined at a point, then a vertical asymptote will occur. So we are going to draw the vertical asymptotes exactly at where the cosine has the x-intercepts. So just be patient with me. I'm going to try to do this as fast as possible. And don't forget to label the asymptotes by their respective equations. So what we have in here is x equals -3 pi over 2, and then x equals negative pi over 2, x equals pi over 2, and x equals 3 pi over 2. Remember that the asymptotes will also redefine the domain of the reciprocal of cosine. So in this case, then we're going to say that the domain of this function will be any real number, and we say that it's any real number because the function will be a continuous line such that x is different than wherever the vertical asymptotes occur. So when you think about it, the vertical asymptotes will happen at every multiple of pi over 2. You see that pi over 2 repeats in every vertical asymptote, and what you see in front of it is -3, -1, 1, 3, and as you can imagine, the next vertical asymptote will be at 5 pi over 2, and that is because the coefficients in front of pi over 2 are all odd integers. So we're going to say that x has to be different than multiples of pi over 2, and now we are going to discuss these coefficients. So as you can see in here, the coefficients are -3, -1, 1, 3, and the pattern will continue with all the odd integers. So therefore, we're going to say that an odd integer can be best described by a general variable, which we call n. Now, as we discussed this in class, if you think of an integer that we can represent, for example, we represent it by letter n, we cannot really tell whether the integer is, even or odd. So in order to make this integer even, we add a coefficient of 2. So now we know for sure that 2n is an even number. And to give this number an odd integer value, then we add 1, the smallest odd number. So 2n plus 1 is representative of an odd number, and 2n is a representative of an even number, obviously. So in other words, what we are going to do is try to write the domain in a kind of a fancier way. So this would be 2n plus 1 times pi over 2. Now, next, we are going to look into the maximums of the cosine function. Now, remember that at the maximum, the cosine function has a value of 1. What that means to secant function, which is the reciprocal of cos, is that the secant will have a value of 1 over 1, which is 1. So what that means again is that the points that mark the maximum of the cosine will be points on the graph of the reciprocal. And similarly, we're going to say that at the points where the cosine hits a minimum of -1, which is these points in here, then the secant function, which is the reciprocal of cosine, will be -1. So again, so these points on the graph of the primary, on the graph of the cosine, will be also points on the reciprocal. So now we are going to build the graph of the reciprocal looking at the increasing and decreasing intervals within each section that is defined by the vertical asymptotes. So recall again that if we have to find the reciprocal of an increasing number or increasing value, then the value of the function will be, or the value of the fraction would be decreasing. And when we have 1 divided by a decreasing value, then the value of the entire fraction will be increasing. So we're going to use this to build the shape of the graph. And what we see in here is a decreasing sign function. And therefore, we're going to say that the reciprocal will be increasing. The only way that the reciprocal could increase is by, obviously, passing through this point, which we know is on the graph of the reciprocal, and following the vertical asymptote. Remember to draw the graphs left to right so that you can better understand and get a full sense of the increasing or decreasing nature of the graph in different parts of its domain. Another way of understanding this again is by referring to the y equals cosine x. At this particular angle, cosine of x will have a value of 2 over 5, and you can find this by simply drawing a perpendicular to the y-axis. Remember, this is 1 unit, and 1 unit is 5 squares in this case, so this would be 2 over 5. So this would be the value of y at this particular angle, 2 over 5. And now, to build the reciprocal, you have to flip the fraction. 5 over 2 will be the value of y for the reciprocal, which would be, this is a 2, 2.5 will be somewhere in here. So therefore, the function will have to pass through these 2 points and increase, so that would be the shape of it. So in this section of the graph, the function of cosine is decreasing, which means that the function of its reciprocal will be increasing. So that the only way that we can go around it is this. And similarly, we can reason about where to and how to draw the graph of the reciprocal on the actual values of cosine. So at this particular angle here, the value of cosine is negative, so the value of cosine is negative 2 over 5, which means the reciprocal would be negative 5 over 2, which is negative 2.5, which means that at this particular angle in here, we will see the graph of the function appear somewhere down here. So obviously the function is increasing, as we said. It has to pass through this particular point, which we figured out by using the minimum on the graph of cos. Now, in a similar fashion, we continue with the rest sections of the rest of the sections of the graph. So we have an increasing function, which will produce a decreasing reciprocal and follow the vertical asymptote. So here we have increasing cosine, that means decreasing secant. And then we have decreasing cosine, that will make an increasing secant. Again, decreasing cosine, increasing secant. And increasing cosine, decreasing secant. Again, as I mentioned, always draw the graph left to right to create a better sense and a better feel of the increasing and decreasing intervals. And lastly, we have increasing cosine, decreasing secant. And this would be the graph of the secant function. So the main features of this function are the domain, obviously, will be restricted by the vertical asymptotes. And in this case, we do not have a max or a min, but we do have local min and local maximum points. So these points that served as maximums for the graph of the cosine x will serve as the local minimums because they're turning points, right, for the function of its reciprocal y equals secant. So this is a local min, a local min, a local min, and down here we have a local max, again turning points, but they're going upside down, and a local max. And obviously we do not have absolute min and max because these graphs will increase to infinity and decrease to negative infinity. And this is a graph of the secant x, and you can complete the chart in here at your own free time, or you can use the chart to draw this graph independently to add more understanding of the graph of the secant function. So thanks for watching again, and I hope this all made sense and it helped you understand how to build the reciprocals. Bye for now.